Hello everyone, this lecture is about continuous time LTI systems and deriving the output from arbitrary input to these systems, characterizing the output, and to do so we're going to define convolution integral, and then we're going to talk briefly about how to compute convolution integral. So again, here we have an LTI system, continuous time LTI system, and we have a continuous time input. We want to find out what output is. Can we easily calculate the output based on the input or not? So to do this, so remember that we defined delta delta when we were introducing unit impulse. We introduced this delta delta of t, which is this very short impulse whose width is delta and whose height is 1 over delta, and delta is a very small number. And we viewed as the impulse, the unit impulse, as the limit of these delta deltas as capital delta goes to 0. So having that in mind, so for a smooth function, for a smooth signal xt, we can approximate xt with this summation of xk delta times delta t minus k delta. What is, so let's see what is this thing. What is this delta times delta capital delta times t minus k delta? So delta, capital delta times delta capital delta is basically this pulse with the height 1. And when we are looking at it at time t minus k delta, we're just shifting this to k delta. So it's basically a short pulse with the height 1. This whole quantity is signal is going to be actually a very short signal pulse whose height is 1 and it is located at time k delta. When we are multiplying it by xk delta, it's going to be a very short pulse with the height of xk delta and with the width of delta. So it's basically, if this is k delta, it's going to be the value of the input, which is xk delta, times that, which is exactly this picture. And if we add, it's going to be this particular pulse. And if we add all these samples, all these short pulses, we get this piecewise constant approximation of xt. And when delta is very small and xt is smooth, this is going to be a very good approximation of xt. So now let's define h capital delta of t to be the response of the system to delta capital delta of t. Then, very similar to the discrete time system, we're going to have the output for delta delta t minus k delta, which is just the shifted delta to time k delta, would be shifted h delta to time k delta because of the time invariant property. And because of the linearity property, so these terms, delta times xk delta, when k is fixed, is going to be some constant. So x of k delta is the value of the input at time k delta. It's going to be a number, and times delta, it's going to be, the whole thing is going to be a number. So that value, alpha, call it alpha times delta delta t minus k delta, would result, because of the linearity, would result to alpha times delta delta t minus h delta t minus k delta. And if we add everything together, we're going to get the output, which is going to be a summation of xk deltas times delta times h delta t minus k delta. So if we let delta go to, capital delta go to 0, as we discussed this when we were introducing unit impulse, this delta delta is going to go to unit impulse. And x hat is going to be a better and better approximation of xt. So x delta is going to be, x hat is going to go to actually xt as delta goes to 0. And this sum if you think about it, this is nothing, this sum of y, the sum that describes y hat of t is nothing but a Riemann approximation of the integral x tau h of t minus tau d tau, where ht is, this is the response to delta t. So as delta goes to 0, or what we're having is nothing but really, for yt, we have nothing but this particular integral. So if we define the output of the system for particular input unit impulse to be h of t and call it the impulse response of the system, then we have this important relationship that the output of the system for any arbitrary input is going to be this integral, which is the integral of the input, times ht minus tau, the d tau. And this integral is called the convolution integral, and it's very similar to the convolution sum. So we're just replacing this sum with the integral. And we denote it using the same notation. So yt is xt star ht. And we have this relationship. Now, how to compute continuous time convolution? It is exactly the same process as the discrete time convolution. So we fix the time that we want to calculate the output at. So we fix time t, and then the rest of this relationship we interpret it as a function of tau and see what's happening as a function of tau. And as a function of tau, x tau remains the same, and ht minus tau, very similar to the discrete time case, is going to be h tau flipped, shifted to time t. So again, t is fixed, so you're like looking at the output at time 2. So ht minus tau, h2 minus tau is going to be h tau flipped, shifted to time 2. And then finally what we're going to do is that we're going to do sample by sample multiplication of ht minus tau and x tau, and then we integrate the whole thing over time instead of adding it. So it's very similar to the discrete time setting. Instead of integrating, we're going to do summing. So x tau multiplied by ht minus tau, and ht minus tau is flipped, h tau flipped, shifted to the time t, and we do sample by sample multiplication, integrate the whole thing, and this will give us the output at time t. And then so we swap time t, we're going to get the output for any given time t. So this was the discussion on output of continuous time LTI systems to arbitrary input and the convolution integral of the input and the impulse response, and how to calculate the convolution integral. Thank you for watching this video.